Hello and welcome back to another video with It's Dr. Dan, and today we're going to be learning about different types of conversion factors that you're going to be finding in chemical formulas. So this is going to be mainly a practice problem video where we go through all the different types of conversions that you might see revolving around a chemical formula, where we can try to define all these kinds of conversion tools. Let's go through a bunch of different practice problems. So let's take a look. We're going to go through how to use mole maps, and we're going to be trying to decipher and go through all these different types of word problems. Let's take a look. Now, when we are doing all these different types of problems, the goal here is to map them out. We want to be able to show how we're going to be converting our units. Our ultimate goal is to let your units guide your process so you can see how they cancel out. Now, when we're doing these conversions, your goal is the mole, meaning that if you can convert to moles, you can essentially map your way to any different type of units in a chemistry course when it involves a chemical reaction or a chemical formula. So the first thing is that we learned about is when it came to moles was that we are essentially having this little simplified term that allows you to convert between moles and atoms. Now, what exactly did we do when we were trying to convert between these two different units? Well, this is when we were using Avogadro's number, which usually we show by N and then an A to help show that, which Avogadro's number was 6.022 times 10 to the 23rd. Okay, so we'll put that here, 6.022 times 10 to the 23. And that is particles per mole. Okay, so that was a very important conversion. And that was something that you could flip, you could take the reciprocal of, and allowed you to simplify the number of atoms you have in a sample, right? Because if we take a little, let's say the little tip of a pen, and we were wondering how many atoms there are on that little tip, there are trillions upon trillions, right? And trying to count those every time is a little cumbersome. So that's when we use moles to help simplify that. Now, being that when we do have moles as well, the other thing we can convert to was mass. Being that we are working in the laboratory environment, we can always measure the mass using a balance. So, how could you convert to there? Well, that was using the term known as molar mass, which you can gain from anywhere on your periodic table. So, if you look at any element that is on there, you will quickly see that you could read all the different conversion terms that are available to you. All of them, like let's say carbon is 12.011 grams per mole, oxygen's 15.99 grams per mole for that element, and you are able to convert between all of them. Now, what other things can you convert to as well? Well, we also learned about trying to read a chemical formula. And essentially, you have subscripts within all those different values. So those subscripts represent the number of moles that you have between two different species. So the mole to mole conversion is something else that is possible by reading your chemical equations. So these are from your subscripts. So that's what allows you to go from one substance to another. So from a molecule and compound to maybe an atom, maybe to a different atom. There are bridges that exist. Now, is that all you can do is just go to the bigger to smaller picture between compounds and molecules? Well, you can also use Avogadro's number to try to calculate the number of compounds, the number of molecules. You can use the molar mass to figure out how many grams of a molecule do you have. The map here is something that you could use to try to figure out how to do all your conversions. So that way you're not overwhelmed when you're going through all of them because there's a lot that you have to go through. And this is what the goal of this video is, to practice these. So we're going to go through many examples using our molar map. The first problem, calculate the mass of 0.453 moles of calcium nitrate. So the first thing you want to do is, what is your map? How can you try to see what these units are? Well, first thing is what exactly are we starting with? So you can see in this problem, we are starting with moles of calcium nitrate. And what is your desired in this problem is you want grams. So how can we try to map that out? Well, using from earlier, right, we saw that we can go between moles and grams using molar mass. So as usual, we want to let our units guide our process to set up these different conversion factors. So if we are starting with calcium nitrate, so CaNO3, 2, what we need to do is convert this to grams. So the way that we're going to do this is by using the molar mass of calcium nitrate, meaning that being that we have our formula, which is CaNO3, 2, we are going to be adding up all of these components. So we have 40.08 grams per mole. We're going to add that times 2 nitrogens. So we have 2 of those, and that's due to the subscripts that are in these equations, right? So that gets distributed. So 2 times 14, 007. And then we're going to add that to the 6 oxygens that are in this problem. All right, so when we have that for all of our values, what we are going to be getting for our molar mass is 164.008 grams per mole. And we're not going to round it just yet. We're going to round it at the very end of our problem. So that way we have all of our units and sig figs correct at the end of our problem. Now, where exactly do I plug this in? How do I let the units guide my process? Well, the thing is, being that we need to cancel our units, we would need to have moles on the bottom and grams on top. Being that moles here is going to cancel moles of calcium nitrate. So these are all going to cancel. Now, being that this is molar mass, that's going to be essentially our value 164.008 all over 1 mole. And those will both these terms all cancel, leaving us with calcium nitrate in grams. So once we solve that, what we are going to get is 33 grams of calcium nitrate, and we're going to round that to 3 sig figs to get 74.3 grams for our final answer. Okay, so we are going to be rounding that, and what is that representing? That is 74.3 grams of calcium nitrate. Let's go on to our next problem, see what other types of things we can try to calculate for here. How many sodium atoms are in 3.73 grams of sodium nitride? Map out your problem. So what did we start with? Well, the first thing is we have one of our masses that's here. So we have the mass of sodium nitride, which is a molecule. So we start with grams, and what are we going to do with that? We're going to convert that to moles of Na3N. So what do we need to first do is we need our molar mass in order to convert that. And then what we need to do is, being it's asking for atoms in this case, we have to read the problem very carefully here. Atoms and molecules are not the same thing. They're individual components of each other. So what we're going to have to then do is do the mole to mole ratio to go to moles of sodium in this case. And then get to atoms, which are our last step, we'll use Avogadro's number to get to essentially how many atoms there are. That's a little bit of a long problem. So let's try to take a look. So the first thing what we want to do is we want to add up our molar mass. So essentially you'll take 3 sodium atoms. So we'll do 3 times 22.99, add that plus 1, 14.007. And what we are going to get for our molar mass is 82.997 grams per mole for our problem. Now, being that we have our first value here, which is 3.73 grams, how exactly can I cancel this out? Because our molar mass is grams over mole. How can we do that? Well, one thing you are allowed to do is take a reciprocal of different fractions. So what is a reciprocal? Well, you can flip a fraction upside down, meaning let's say if I have the following here, I have 3/5. I could flip it, right? So you don't literally want to flip it upside down like I did over here. You want to put it as 5/3, taking your reciprocal, meaning we can do the same thing here. So if I had 82.997 grams per mole, I can write that here on the bottom and put 1 mole on top, which is the reciprocal of my molar mass. Now, why is that really good for us? Well, essentially, it allows us to cancel out grams in this part of the problem. Now, one thing we want to make sure that we are doing here is that we are keeping track of all of our different molecules that we have because we are trying to get to moles of sodium. So our next step was to go do the mole to mole conversion, which was to get to sodium atoms, which for every 1 mole of sodium, I have 3, or sodium nitride, I have 3 moles of sodium. How did I get that? Well, that's coming from the subscript that is in the problem. So it's a 1:3 ratio we're counting. Now, once we do that, our next step is being that we have our moles of sodium. That's equivalent to 6.022 times 10 to the 23 atoms sodium. And the one thing we're going to notice here is that, oh, all these different terms, everything's going to cancel out very, very nicely. Look how our units guided our process to sodium atom part. So when we try to plug this into our calculator, we're going to take 3.73 times 3 times 6.022 times 10 to the 23. Take that number and divide it by 82.997. And then what you're going to get for your answer is you're going to get 8.1210 times 10 to the 22 atoms of sodium. And being that we started with 3 sig figs, we would need to round that down to 3 significant figures. Okay? And that would be your final answer for this problem. Let's take a look at another example of doing these different types of calculations. A sample of tin fluoride or tin 4 fluoride contains 4.62 moles of tin. How many moles of fluorine do you have? What is your map? Okay, so when we are trying to do this problem, what are we exactly starting with? We are starting with 4.62 moles of tin in this problem. So what we are going to want to do is to go from moles of tin and convert that to essentially moles of fluorine in this problem. How exactly can we do it? Well, once again, we can represent this with our subscripts. There are different conversion terms we can actually gain by reading this chemical equation up here. So what can we get from that? Well, just to represent that, just so you can see, we can say that for every 1 mole of tin, I have 1 mole of SnF4. I can also say that for every 4 moles of fluorine, I have 1 mole of SnF4. We can also say that for every 1 mole of tin, I have 4 moles of fluorine. So there's relationships within all of these that we can try to use to determine how do we want to convert? How do we want to try to cancel out our units? So being that we started with 0.462 moles of tin, what we are going to want to do is cancel out our moles of tin. So how do we have that? Well, 1 mole of tin is equivalent to 4 moles of fluorine. And we can see that, oh, this is a pretty quick problem. Moles of tin cancels moles of tin. And what that's going to be is 0.462 times 4 for our problem here. And that's going to give us our final answer. So when we do that, okay, with these kind of problems, we have to pay attention to the terms that are being set for us. What is the mass in kilograms of S2F3, which contains 4.89 times 10 to the 26 atoms? Okay, so what exactly does that mean by atoms in this case? It doesn't exactly specify anything. And notice how it doesn't use molecules or compounds. So what does that mean here, being it doesn't specify? This is all of sulfur and fluorine atoms in this problem. Sometimes they might say like maybe atoms of sulfur, sometimes of fluorine, sometimes it's generic, meaning that this is all of the atoms indiscriminately all being placed within this problem. So what we're going to be doing here is we're going to go from atoms to moles of atoms. So how many different types do we have here, or individual ones from our subscripts? So one thing you can see is that, okay, there's 5 different atoms by adding up our subscripts, which is equivalent to 1 molecule that is here. So that's going to be 1 mole for every 1 molecule. So we can use that for ourselves. Um, then what we're going to be doing is being that once mass, we can then say that, all right, well, 1 mole is equivalent to whatever to the molar mass of the compound. And then then that will give us our grams in the final part of the problem. So this is a little bit of a weird one, a little bit of a tricky one, but it's something that we want to make sure that we can see and try to map out for ourselves. So the first thing let's do is let's get the molar mass done. This is a skill that you will use a lot in a chemistry course. So you want to try to be very, very fast when it comes to looking up your different molar values and adding them up quickly. So we have that 32.06 times 2, and then we're going to add that to the molar mass of fluorine, and being that there's 3 of them, what we are going to end up getting from this part of the problem is that we have a molar mass of 121 and a 114 grams over moles. So this is what we're going to be using in our problem. So we'll save that for later. So the first thing what we're going to do is we're going to start with our number of atoms, right? We have 4.89 times 10 to the 26 atoms. And we're going to slowly work our way across and try to convert all these different units. So we have our Avogadro's number, which is going to go in the denominator here to cancel out atoms. And that is equivalent to 1 mole of S and F. Okay. Now, when we have that atoms cancels atoms, now what we're going to be doing is we have 5 moles of S and F. And that was from our different subscripts here. And that's equivalent to 1 mole of S2F, or F3, not 6. So that's our molecule. And we can see that those units also cancel, right? Oops. So then afterwards, what we will then do is use the molar mass that we got to convert moles of S2F3 to our grams, which from before we had for every 1 mole, we have 121,114 grams of S2F6. All right, so now that we have that, we are going to cancel all of our units, prove and show that. All right, now once we do the math here, what we're going to be doing is taking that 4.89 times 10 to the 26, multiply that by 121.114, and then divide that by 6.022 times 10 to the 23 times 5. So you're going to get a pretty big mess of a problem. Now, when you get your final answer, you should get this in grams first, and you're going to get 19,669 grams of S2F6 in your problem. Now, being that we want this in kilograms, we're going to divide that number by 1,000, because 1,000 grams is equal to 1 kilogram. And then we're going to be rounding that to 3 sig figs again for this problem. So you'll have 19.7 kilograms is your final answer in the problem. Okay, let's go on to another type of problem that you might see. How many atoms of oxygen are found in 48 grams of oxygen gas? Okay, so being that we are doing oxygen gas problem, we're starting with a mass. One thing you got to be able to identify is what is its natural form? So oxygen, what do you breathe? Well, you breathe out oxygen, but what form does it take up? It's O2, right? So it's one of your diatomic gases, right? So you remember, have no fear of ice cold beer. The of part of that is O2. So what that means is for every there are 2 moles of oxygen atom inside of every 1 mole of O2. So we got to kind of keep that in mind, that there's a conversion that's hidden in plain sight here. So the very first thing that we are going to be doing in our roadmap is that what we've done in the past here. We're going to start with the always a term that's given to us, which is 48.0 grams of O2. How do we cancel out those grams? Is we're going to be using the molar mass of O2. So 1 mole of O2 is equivalent to 15.999 times 2. So when we go through that value, we're gonna roughly just kind of round that here just while I write it down. So roughly about 32.00 grams over 1 mole. You could add it up and you'll get about 31.99 something, but we're just gonna round it for time's sake. Now the big thing is here, we want to make sure our units cancel. So notice how I have grams written on top and the units don't cancel. So you want to switch those up and kind of make sure that you take the reciprocal like we've been talking about. So grams cancels grams. Now we want to use that conversion term that we defined earlier, which was 1 mole of oxygen is equivalent, or oxygen gas is equivalent to 2 moles of oxygen atom. Now, when we do that, we can see that our units cancel again. Great. And now, being that we want to know how many atoms, this is when we use Avogadro's number to define how many atoms we have in our problem. Okay, and then we see that atoms cancels again. And this will give us our final answer when we do our math multiplication here. So we multiply all the values on top, divide what's on the bottom, and then what we are going to be getting for our final answer is 1.81 times 10 to the 24 atoms of oxygen when you do those mathematics. Let's go on to our next problem. Dinitrogen monoxide, N2O, also known as laughing gas, is used as an anesthetic in dentistry. How many grams of nitrogen are in a 340 gram sample of N2O? So being that we are starting with a mass, the first thing that we are going to need to do is cancel out grams. So what's the first conversion term that should come to mind in order to do that? Well, this is when we use our grams to moles. So let those units kind of guide your process. You're thinking, right? Grams of N2O is equivalent to 1 mole of N2O. Now, what will we do after that? So that means we need to define the molar mass here. We have for every 1 mole of N2O is that there are 2 moles of nitrogen. And being that we want to get into grams of nitrogen, we'll have 1 mole of N is equivalent to 14.007 grams of N. So the one thing that we need to do is calculate our molar mass of N2O. So what we're going to do is take 2 times 4.007, add that plus 15.999 grams per mole. And what we are going to end up getting is 44.013 grams per mole for N2O. So we're going to plug that value in, 44.013, and then we're going to proceed and do our calculation here, where we take 340 times 2 times 14.007, and then divide that by 44.013. And what you will get for your number is 216.4 grams of N for nitrogen. And then we're going to be rounding that to 3 sig figs for 216 grams of nitrogen. Noticing like all my problems are 3 sig figs. They're not always 3 sig figs. It just happens to be that many of the ones I went over in this video are 3 sig figs. Let's go on to another problem that you could see, and this will be your last one for this video. Thank you so much for listening so far. What is the volume of 7.10 moles of sodium hydroxide, assuming a density of 1.21 grams per milliliters? Okay, how exactly do we do this one? This one's a little different. So it's combining concepts that have been gone over in chemistry. So the first thing that we have, looking at the problem and deciphering this, is we have 7.10 moles of sodium hydroxide. And we also have a conversion term that was given to us, which is the density. So how can we map out the units? Well, we have moles, and we also have grams over milliliters. So what's the commonality behind those two units? Well, one thing that we can do is we can convert this to grams, right? Because we have molar mass, Avogadro's number, and mole to molar ratio. Those are your three choices. So if we can convert this to grams, then what we can do is use the density afterwards to bridge the gap to milliliters, right? So then what that's going to do is it's going to give us the units that we want. So what do we need to define for ourselves is we need the molar mass for sodium hydroxide. So let's do it. So what we're going to do is we're going to add up all these elements here. So we have 22.99 plus 15.99 and plus 1.008. And what we're going to get is 39.997 grams over moles. And that's what we're going to use above for our molar mass of sodium hydroxide. Okay. So first thing, what we said we're going to do is we're going to use our moles that we were given in the problem. So which was 7.10 moles of NaOH. We will then put our molar mass in, which is 1 mole is equivalent to 39.997 grams of sodium hydroxide. And then what we will do is use our density, which is 1.21 grams is equivalent to 1 milliliter. So this is why we map out all of our units, because it allows us to be able to make a plan for ourselves. And the more you do this, the easier it's going to get. So you want to try to practice it as much as you possibly can. It's something that's used throughout all of chemistry, and you want to try to get really, really comfortable solving for those units. Now, when we plug this into our calculators, what we will get is 234.69 milliliters. And we are going to once again be rounding that to three significant figures because we started with three sig figs, which is 235 milliliters as our final answer. Just keep in mind, the goal is the mole when we're trying to map these out. So you want to be able to use your different molar masses when you're trying to solve them. So don't be afraid to just dive in there, try as many as you can, keep practicing, and learn your conversions so that you know them like the back of your hand. Thank you so much for listening. I hope this video helped. And please stick around and like and sub if you haven't yet to see even more content on the channel. Thank you so much. I'll see you all later. Bye now.